This is one of the chapters that you have for your second term exam, the year 2021-2022. So the syllabus for this chapter has all the functional groups that we've learned up until now. This also includes the nomenclature, the classification, the structure, methods of preparation, physical and chemical properties, uses, identification of primary, secondary, and tertiary amines. And for this year, you will not be learning diazonium salts. So let's begin. Ammonia's formula is NH3. When the hydrogen atom of NH3 is getting replaced by an alkyl or an aryl group, we get amines. So generally, amines are considered derivatives of ammonia. Here you have a few examples. Here you have a methyl group which has replaced a hydrogen atom in the ammonia. Here you have benzene ring, which has replaced a hydrogen atom. Here you have two methyl groups, and here you have three methyl groups. So amines are generally considered as the derivatives of ammonia. And and the NH2, that is the amine group, is present in a lot of biologically important compounds, like our amino acids. All of the amino acids consist of an amine group, as you have learned in biomolecules chapter, which you probably learned for the previous term. So amine group is very important, and we'll be learning about right from the nomenclature to the chemical reactivity of amines. Nitrogen, as we know, is trivalent in nature, which means it can form three bonds. So that's why you have NH3, right? So in amines, the nitrogen atom is sp3 hybridized, okay? And each of these sp3 orbitals are going to overlap with either an alkyl group or a hydrogen based on the kind of amine that is formed. We will be learning about the classification in a bit, but the overlap with the sp3 hybridized orbital is going to be with either the alkyl with another carbon atom, or it's going to be a hydrogen atom. If it's a carbon, it's going to be an alkyl group or an aryl. Whereas if it's a hydrogen, it's just going to be that particular atom. The fourth orbital, on the other hand, will have two lone pairs of electrons. Sorry, a pair, or rather a pair of electrons. There is two electrons on it. And this particular molecule, that is triethylamine, you can see that the bond angle is 108. So generally the C and E, where E can be a carbon or a hydrogen based on the kind of amine, the bond angle is less than 109. And this is again due to the presence of the lone pair of electrons. The shape of the molecule is going to be pyramidal. Here you have the example of triethylamine, where the C and E bond angle is 108 degrees. With that, we're done with the structure of amines. So they are sp3 hybridized, shape is pyramidal, and the three orbitals, sp3 orbitals, are going to be used for overlap with another alkyl group or hydrogen based on the amine we are talking about. And the fourth orbital of nitrogen is going to have a pair of electrons, an unshared pair of electrons. And the shape is a pyramidal shape. With that, we're done with the structure of amine. Classification of amines is quite easy. First of all, you have, based on the number of alkyl groups, you have primary, secondary, tertiary. And usually, if you remember, when we talked about alkyl halides, we had it with respect to the carbon atom, but here our functional group is NH2, and based on the number of alkyl groups attached to it, we have primary, secondary, and tertiary alkyl or aryl amines. Now, these two R groups can be same or different, and if they are going to be the same, they are called as simple amines. If the R groups are different, they're called as mixed amines. So that's about it. The classification is quite simple. We're talking about it in terms of the number of hydrogen atoms replaced by the alkyl groups. If one of the hydrogen atom is replaced, it's primary. 2, it's going to be secondary. 3 is tertiary. Not only that, if the alkyl or aryl groups which are bound to the NH or the nitrogen atom, if they're the same, it's going to be called simple amine. If they're different, they're called mixed amines. With that, we're done with the classification of amines. Nomenclature of amines. Like we learn for every other functional group, we'll be talking about both common name as well as IUPAC name. In case of aliphatic amines, the alkyl group is referred to as is basically prefixed to the amine. So here you have a primary amine, that's methylamine, which basically means that it's a CH3NH2. On the other hand, here also you have another amine, that's an ethylamine. So here you have an ethyl group attached to the NH2. Now, when we have secondary and tertiary amines, if you have the same same alkyl group, like in this case, you have 3 alkyl groups and 3 of them are methyl groups. So they are referred to as trimethylamine. On the other hand, if they are a mixed set, the longest chain is considered as the parent chain. So here you have an ethyl group and an ethyl group as well as a butyl group. So the butyl group is considered the part of the parent chain. So NN diethyl butyl amine. Next, for the IUPAC nomenclature, for primary amines, we first refer to them as alkanamines. So here ethanamine. Here, propane 1 amine. The reason we put 1 is because in ethane, it does not matter if it was this carbon or this one, whichever would have been, it would have been called ethanamine because you just have 2 carbon atoms. But when you have propane, then you have the first carbon as a possibility as well as the second one. So you have propane 1 amine or propane 2 amine. So if there are more than 1 amine groups present in different positions of the parent chain, this is going to get numbered. I think you have an example here. No, you do not. So here in this case, you have a CH2, that is that's 2 carbon atoms, which means it's an ethyl group. Here you have one of the amines and here you have the second one, and both of them are primary amines. So basically we'll be numbering the carbon atoms to show the position of the amine groups. So the name of the compound becomes ethane 1, 2, because the first and the second carbon atom has an NH2 and NH2, 1, 2 diamine. And in case of secondary and tertiary amines, we use N to designate the substituent. So here you have N-methyl ethanamine, N-diethyl ethanamine, because all 3 of the ethyl groups are of the same length. So it does not matter which is going to be the parent. 2 of the ethyl groups are considered as the substituent, while 1 is the parent chain. Similarly, in this case as well, you have 2 ethyl groups. So N-diethyl butane 1 amine. The 1 is showing that the first carbon atom is bound to the nitrogen atom. Similarly, I am so sorry, excuse me. Here as well, you have a methyl group and an ethyl group. Since the ethyl group is longer than the methyl, so it's N-methyl ethanamine. And in case of aryl groups, generally the simplest simplest amine, aryl amine, is referred to as aniline. We generally call it as aniline, and most of the time we refer to it by its common name and not its IUPAC name. But its IUPAC name is benzene amine. The E is going to get removed and it's called as a benzene amine. And with respect to the substituents, you can just number it with respect to each of the substituents, and they are referred to as the same. And here you have another example of N dimethyl, which means you have 2 methyl groups attached to the nitrogen and a benzene ring. So the benzene ring is going to be considered as the parent, and you have 2 methyl groups attached to it. So N dimethyl benzenamine. So do check out, do go through the structures and how to write the IUPAC names, because IUPAC names are always very important. With that, we're done with the nomenclature of amines. So we defer it for primary, it's different from secondary and tertiary always. So primary, it's quite simple. We're just referring to the alkyl group and the amine. The E is removed for the alkane. Whereas secondary and tertiary, we are using the letter N to show that the substituent is attached to the nitrogen atom. And for secondary and tertiary, the longest chain is considered as the longest chain of carbon atoms is considered as the parent chain. With that, we're done with the nomenclature of amine. Preparation of amines. Preparation of amines, we have 6 methods of preparation. 3 of them are reduction reactions. That is of nitro compounds, of nitriles, and amines. Apart from that, we have ammonolysis reaction of alkyl halides and Gabriel phthalimide synthesis, as well as Hoffman's bromamide degradation reaction. So let's begin with ammonolysis of alkyl halides. So here what happens is an alkyl or a benzyl halide is going to react with ethanolic solution of NH3, that is ammonia, where the halide group is going to get replaced by the NH2. And this process of cleavage of the RX, the CX bond, is called as ammonolysis. So in this reaction, you have a continuous formation. So first you will get a primary amine. When we take a primary amine and react it with alkyl halide, we'll get the secondary one. And then when it further undergoes reaction to give us the tertiary as well as quaternary ammonium salts. So this ammonium salt, when it reacts with a strong base, it gives us a free amine. So here, if you notice here also, we had a substituted ammonium salt only synthesized. So this is reacting with a strong base to give us a free amine. But the issue with this particular reaction is the fact that, as you know, since it's a continuous formation, there might be a mixture of primary, secondary, and tertiary amine, which is going to get obtained. However, to minimize the formation of other products, that is secondary and tertiary, when an excess amount of ammonia is used, the other two products which are formed is not as much as, we get it in, as we get the secondary and tertiary, we'll get primary as a major product. The order of the reactivity of alkyl halides is going to be Ri is more reactive than RBr, which is more reactive than RCl. So with that, we're done with the ammonolysis. Now, reduction reactions. So here you have a table which compiles all the three. First, let's go over these individually, and then we'll come to this one. So nitro compounds are going to undergo reduction in the presence of hydrogen gas, and the catalyst here is a finely divided nickel, palladium, or platinum to give us amines. So nitro compounds undergoing reduction to give us amines. Now, this is also done with metals in acidic medium. And so in this case, nitroalkanes are giving us alkan amines, right? Here you have two reactions. You have H2 and PD, which is hydrogen and palladium as a catalyst. And this giving us the NO2 has gotten converted to an amine. So we're getting aniline. Similarly, here you've used a mixture of metals in acidic medium. So SN and HCl, or Fe and HCl, that is tin or iron. Here, out of these two, iron is preferred because the FeCl2, which is formed, will get hydrolyzed, and this in turn releases the HCl, hydrochloric acid. And so for this case, the amount of HCl that is required for the reaction will decrease. And so the Fe and HCl is preferred. Now, the next one is the reduction of nitriles. Nitriles are basically RCN. So this RCN is undergoing a reduction to form NH2. Now, you do not have the removal of this carbon atom that we will observe. Okay, that is another reaction, sorry. But here you do not have the loss of carbon atom. So the nitriles are going to get directly converted to amines. The reducing agent used over here is either lithium aluminium hydride, or it can be catalytic hydrogenation reaction. And this is also useful for increasing the carbon atom by 1, and it is used for the ascent of the amine series. Next is amines. RCONH2 is amines. So this is undergoing reduction in the presence of lithium aluminium hydride to give us an amine. Now here you have the compilation of all the three reduction reactions. So the reduction of nitroalkanes, nitriles, as well as amines are going to give us amines. So in each of the case, you have a variation in terms of the reducing agent. Here, however, I forgot to add it. The metals in acidic medium can also be used as the reagent for the conversion of nitroalkanes to amines. So all the three reactions, you have amines getting synthesized. In the first case, we're using hydrogen gas in the presence of a catalyst that is finely divided nickel, palladium, or platinum. Or the reaction can also be done by using metal in a acidic medium. The second case, when nitriles are getting converted to amines, you're using lithium aluminium hydride, or the reaction is conducted by catalytic hydrogenation, which is this basically. The third case, that is amides, we are converting it by using the reducing agent, lithium aluminium hydride. So do not learn all of these individually. If possible, put them all in a table and then learn. That way you might find it much, much, much easier to do it. The next one is going to be Gabriel thalamide reaction. So in this reaction, what is happening is, this is first of all used only for the synthesis of primary amines. So thalamide is reacting with ethanolic KOH, that is potassium hydroxide, to give us the potassium salt of thalamide. This potassium salt of thalamide is undergoing a reaction with a primary alkyl halide. And this is leading to the formation of N-alkyl thalamide. So first, what is happening? H is getting kicked out, K is coming in. So this is leading to a negative charge on the nitrogen and a positive charge on the potassium atom. Next, what is happening? The Rx is going to react with this compound, and what the K is going to get kicked out and R is going to come in. And that gives us N-alkyl thalamide. Now, this N-alkyl thalamide is undergoing a reaction with NaOH, and this leads to the sodium salt of phthalic acid and a primary amine. So this again can be reused. So it's not going to get wasted. It gets reused for for the same reaction over. And the important thing you need to remember is the aryl halides will not undergo nucleophilic substitution reaction. So they will not undergo this particular reaction. So we can't synthesize aryl amines with this method. So what's happening first? Thalamide is this pretty little thing. Okay, you have a 5-membered ring over here. You have a 6-membered ring. Okay, and you first react it with KOH. H gets kicked out. K comes in, so N minus K plus, that's what you get here. And then it reacts with Rx, where Rx is a primary alkyl halide. Very important. It's not secondary or tertiary, it's a primary alkyl halide. And this is leading to the formation of N-alkyl thalamide, basically K getting kicked out and R forming a bond with the nitrogen atom. The next reaction is the reaction with a base to lead us to the formation of the sodium salt of phthalic acid and the primary amine. This reaction is not applicable for the synthesis of aryl amines, because aryl halides do not undergo nucleophilic substitution with the phthalic ion, which is formed. The last one is Hofmann-bromamide degradation reaction, and in this one only you have the loss of carbon atom. So remember, in the previous case we learned reduction of amides. The same thing is happening here. Only issue is the CO is going to get removed. So an amide is reacting with bromine in aqueous or ethanolic solution of sodium hydroxide to give us a primary amine. So this CO is going to get removed and you have RNH2 formed. So the products which are formed are sodium carbonate and NaBr, sodium bromide, and water. So the carbonyl carbon is migrated from, basically the R group is migrating from the carbonyl carbon to form a amine compound. So with that, we're done with the various methods of preparation of amines. We started with ammonolysis, and then we learned about the reduction of 3 compounds, nitroalkanes, nitriles, and amines with the respective reducing agents to lead to the formation of amines. If you notice, you have similarity in terms of the reducing agents which are used. Next, we talked about Gabriel thalamide synthesis, which is used for the synthesis of primary amines, and that's because the reagent we are using is going to be a primary alkyl halide. Next, we learned about Hofmann-bromamide degradation reaction, which also involves an amide, but the number of carbon atoms in the formation in the product is 1 less than that of the amide that underwent the reaction in the first place. With that, we're done with the synthesis or preparation of amines. Physical properties of amines. Let's start with state. Gases with fishy odor are going to be lower aliphatic amines, whereas primary amines which have more than 2 carbon atoms are liquids, and higher amines are solids. Aniline, aryl amines are actually colorless, but when they are stored for a long period of time, they tend to undergo atmospheric oxidation and they become colored. Next is going to be solubility in water. Like we learned for the other functional groups, lower amines are soluble in water. And this is because of their ability to form hydrogen bonds. Now, when obviously the molecular mass is increasing, the solubility is going to decrease because of the length of the hydrophobic chain. Now, when we compare alcohols and amines, oxygen atom has a higher electronegativity than a nitrogen atom. So nitrogen atom's electronegativity is just 3, whereas oxygen is going to be 3.5. Because of that, the alcohols are able to form hydrogen bonds much more effectively than amines. And this makes the alcohols are more soluble in water than that of amines. This is again due to the formation of hydrogen bonds. In case of alcohols, the hydrogen bonds are much stronger, whereas in case of amines, they are weaker than that of alcohol. So alcohols are more soluble in water than amines. Solubility in organic solvents, similar to what we study about other compounds. Amines are soluble in organic solvents like alcohols, ethers, and benzene. Next, boiling point. Now, boiling point, again, we will be talking about it with respect to hydrogen bonds. Now, primary amines have 2 hydrogen atoms. Secondary amines have 1 hydrogen atom, and tertiary has no hydrogen atoms attached to the nitrogen. So, a hydrogen bond is formed between the hydrogen atom of one molecule of amine and the nitrogen of the other molecule. And since you have 2 hydrogen atoms in a primary amine, the tendency to form a hydrogen bond is much stronger. So they tend to form much higher hydrogen bonds than that of secondary. And since tertiary does not even have a hydrogen atom, the hydrogen bonds are not formed in this case. And due to that, the boiling point is affected. So boiling point is high for primary amines than that of secondary. And then you have tertiary amines. So that is the order of boiling point. We have primary more than secondary, which is more than tertiary. The reason being the number of hydrogen atoms. Primary has 2 hydrogen atoms, secondary has just 1, tertiary has none. And the ability of the hydrogen bonds determines the boiling point. More is the ability, more is the boiling point. And so primary amines have a higher boiling point than secondary, than tertiary. With that, we're done with the physical properties of amines. 2 important things: solubility in water. Lower amines are soluble in water. And as the size of the molecule is going to increase, the solubility is going to decrease. When we compare alcohols and amines, due to the higher ability or a higher tendency of an alcohol to form a hydrogen bond, stronger hydrogen bond, due to the fact that oxygen is more electronegative than nitrogen, alcohols are more soluble in water than amines. Whereas in case of boiling point, you have a similarity in terms of hydrogen bonding here as well. So primary is having 2 hydrogen atoms, secondary has 1, and tertiary has none. And because of that, the extent of formation of hydrogen bonds is higher in primary and secondary than tertiary. And due to that, the boiling point order is going to be highest for primary amines, then you have secondary, then you have tertiary. With that, we're done with the physical properties of amines. Chemical properties of amines. So the reactivity is due to 2 reasons. First is going to be the difference in electronegativity between hydrogen and nitrogen, and the presence of unshared pair of electrons on nitrogen atom. So there is going to be a huge difference in terms of reactivity between primary, secondary, and tertiary due to the difference in hydrogen atoms. Not only that, amines also have a tendency to behave as a nucleophile because of the lone pair of electrons. If you remember, when we studied about alkyl halides or haloalkanes and haloarenes, and there were nucleophiles, the set of nucleophiles written in that table, one of them is an amine. So let's start with the chemical reactions of amines. We are going to be starting with basic character. So amines on reaction with acid lead to the formation of salt. So this means amine is going to act as a base. Not only that, when amine salt is reacting with a base, it is forming the parent amine. If you remember, this particular reaction was also studied when we talked about the ammonolysis of alkyl halides. The amine salts are not only soluble in water, but they are also insoluble in organic solvents. And this reaction can tell us that the it is able to help us distinguish between the non-basic organic compounds which are insoluble in water. Now, amines also react with mineral acids to give ammonium salts, and all of these show that amines are basic. So, amines are reacting with acid to form a salt. When they're reacting with mineral acids to form ammonium salts, and the ammonium salt, which is formed, is reacting with a base to form a parent amine. Now, they also act as a Lewis base. And when they act as a Lewis base, they have a tendency to accept a proton. So we are able to understand that with their Kb and pKb values. Now, this is the K value, which is going to be the products by the reactants concentration. And since the H2O is considered to be a constant, we basically incorporate it into the value of K, and we get the Kb value as RNH3 plus into OH minus by RNH2 concentration of each of these. And pKb is going to be minus log of Kb. That is the negative logarithmic value of Kb. Now, larger the value of Kb or smaller is the value of pKb, we will have a strong base. Large value of Kb, small value of pKb, we are getting a strong base. Now, for aliphatic amines, it's going to be ranging from 3 to 4.22. Now, the reason you have aliphatic amines more basic than ammonia is because of the fact that when, here you have a comparison between an aliphatic amine and ammonia. So when they act as a Lewis base, what they're going to do, they're going to accept the proton, and these two are going to be different with respect to their stabilities. Now here you have an alkyl group, whereas here you just have a hydrogen atom. And we know alkyl groups have a tendency to donate or to release electrons. So they're electron releasing in nature. Now this electron releasing nature of the alkyl group will stabilize the positive charge on the nitrogen atom. Whereas here you just have a hydrogen, and that's not going to stabilize the nitrogen as much as the alkyl group does. So because of that, you have the alkyl aliphatic, or rather aliphatic amines being more basic than ammonia. Not only that, the issue was also the aromatic amines are going to be less basic than ammonia because aromatic groups are electron withdrawing in nature. Now, apart from the inductive effect, you have other effects like solvation effect and steric hindrance that will affect the basicity of amines. So before we start with studying about the basicity in detail, you need to remember this formation of a formation of the cation and the stability of this cation is what decides the basicity of that particular compound. Now, when we talked about plus I effect, that is the inductive effect shown by the alkyl groups, that obviously implied that a tertiary amine is going to be more basic than secondary, than primary, than NH3. This is observed in the gaseous phase. But for some reason, the same thing was not observed in the liquid phases. Now here you have methanamine. Okay, methanamine is, so the pKb values are given, and it has a smaller pKb value than N-diethyl methanamine. So there was something going on. They wanted to figure out why. So there are two reasons. First is the plus I effect of alkyl. Two things happening when we're talking about basicity. First is going to be the plus I group, plus I effect. So the alkyl groups are electron releasing in nature, and they tend to stabilize the cation which is formed. Not only that, there is something called as a solvation which is observed. Now, what happens during solvation is that there is an interaction between the amine and the water molecule, and this will lead to the stability. Okay, and bigger the size of, or the greater the size of the ion, less will be the solvation, and to less extent it's stabilized. So let's talk about solvation again in detail. Now, amines, as we know, when they dissolve in water, they tend to form hydrogen bonds. Why? Because of the electronegativity of the nitrogen atom. They form a hydrogen bond with the water molecules. Now, there is some amount of energy which is released during the course of the formation of a hydrogen bond. And this is called as the hydration energy. And because of that, the amine is going to get stabilized. So to more extent that we have the formation of hydrogen bond, more will be the stability of the cation. And so because of that, when the amine will will gain a proton and lead to the formation of a positive charge, more will be the ability for it to form that because it's going to be more stable. So this is especially observed when you have a smaller sized ones. Like, if or rather when we talk about primary, it has three hydrogen atoms. So two hydrogen atoms, and they have the ability to form hydrogen bonds to more extent compared to secondary and tertiary. That's what we studied when we talked about the boiling point of amines. There is another factor that we have to consider. That is steric factor. Now we know alkyl groups are bigger than a hydrogen atom. So bigger alkyl groups means that they will affect the ability of an acid to come and attack the lone pair of to attack the amine. And this in turn will lead to a decrease in the stability. And that is why the tertiary alkyl amines are least basic. So with respect to the plus I effect, we can say that the tertiary amines should be more basic than primary and secondary. But because of solvation of ions as well as steric factors, it's actually primary being more basic than secondary, or rather it depends upon the size. In this case, it is secondary is more basic than primary, which is more basic than a tertiary. Okay, whereas in this first case, when you have an ethyl group, you have again the secondary more basic than tertiary, which is more basic than primary. So it varies due to two reasons: solvation and steric factors. If we had just considered the plus I effect shown by the alkyl groups, then it would have been tertiary more stable than, tertiary amine more basic than secondary, which is more basic than primary. But that's not the case. And there are two other factors that's happening, and that is solvation of ions and steric factors. So when an amine is getting dissolved in water, it forms a hydrogen bond. More is the extent of formation of hydrogen bonds, more is going to be the stability of the cation formed. I should stop saying carbocation. I know, I'm sorry. Next is steric factor. The bulky groups will make sure that the acid is not able to come and attack the amine, and this in turn will make sure that the basicity is going to decrease. Next is going to be aryl amines versus ammonia. Now, aryl amines are less basic than amines. As we know, that's because of the high pKb values. Now, when the NH2 is attached to the benzene ring directly, it is electron releasing in nature, and the negative charge is going to get, or rather, the ortho and the para position are going to get a negative charge, and you have like 5 resonance structures forming. Now, when this NH2 accepts a proton, it leads to formation of the anilinium ion. Okay. And what happens is, in anilinium ion, you just have 2 resonance structures forming. And so the stability of the anilinium ion is less than that of a aniline. And so the basic nature will be less than that of ammonia. Okay. Normal conditions, we know aniline is stable, but when you have the NH3, the anilinium ion forming, that's what is considered for the stability, or rather, that's what is considered for the basicity of amines. And because of the formation of just 2 resonance structures, aniline is not as basic as ammonia. Next, obviously, substituted anilines, where you have electron releasing group, they will increase the basic strength, whereas electron withdrawing groups will decrease the basic strength. Next is alkylation. Amine is reacting with an alkyl halide, and then it's undergoing alkylation. If you remember, that's what we studied in the preparation of amines. The first one, a monolysis of alkyl halides. That is exactly what we studied. Primary amine is undergoing reaction with alkyl halide to give us a secondary. Secondary is giving us tertiary. Tertiary is giving us quaternary ammonium salt. The next reaction is acylation reaction. Now, what happens is, aliphatic or aromatic primary, secondary, tertiary amines are reacting with acid chlorides, anhydrides, or esters. And they undergo a nucleophilic substitution reaction, and this is also called as an acylation reaction. Now, the product which is formed is an amide. So what's happening over here is the NH2 group, the hydrogen of the NH2 or NH is replaced by an acyl group. Sorry, this does not include tertiary amines. I'm really sorry. So aliphatic, so they undergo reaction to give us an amide. So the hydrogen atom is getting replaced by a acyl group. So the reaction is going to take place in the presence of base, which is going to be much stronger than an amide, than an amide, and this makes sure that the base is going to help remove the HCl which is formed, which makes sure the reaction goes in the forward direction. So here you have various examples of reactions taking place. You have ethanamine reacting with CH3COCl, and acyl chloride. And this is leading to the formation of this particular compound, which the negative charge goes in, it loses an HCl and leads to the formation of N-ethyl ethanamide. Similarly, you have another reaction where this is a secondary, this is primary. So when the secondary undergoes the same reaction, you have a new bond formation between nitrogen and the carbon, the carbonyl carbon. And the byproduct in these reactions is HCl. On the other hand, when it reacts with an anhydride, it also leads to the formation of the same kind of compound, but the byproduct which is formed is a CH3COOH, which is an acid. Okay. Next, amines are also reacting with benzoyl chlorides to form an amide, and this reaction is called as a benzylation. So methanamine has undergone reaction with benzoyl chloride to lead to the formation of N-methyl benzanamide. So here also the Cl is going to get kicked out and one of the hydrogens is getting kicked out and there's a new bond formation between the carbon and the nitrogen atom. The next reaction we're going to be studying about is carbylamine. Now carbylamine and reaction with nitrous acid as well as reaction with aryl sulfonyl chloride are used for us to differentiate between primary, secondary and tertiary amines. So carbylamine reaction is observed only in primary amines. So this is not observed for secondary or tertiary, it's only for primary. So they undergo so primary aromatic or aliphatic amine is reacting with chloroform and ethanolic potassium hydroxide to lead to the formation of isocyanide. Isocyanide is also referred to as carbylamine and it is having a foul smell. There are other products which are formed, potassium chloride as well as water. Secondary and tertiary do not undergo reaction here. So this is used for us to identify a primary amine. So aliphatic or aromatic primary amine is reacting with chloroform and ethanolic potassium hydroxide. They're heated for us to get an isocyanide or carbylamine. Next is reaction with nitrous acid. Again, different types of amines will react differently with nitrous acid. First of all, nitrous acid is formed by reacting a mineral acid and a sodium nitrite. So primary aliphatic amine is reacting with nitrous acid to give us a diazonium salt, which is unstable. And this in turn gives us nitrogen and alcohol. Now, this nitrogen which is formed is quantitatively estimated for us to figure out the amount of the amino acid or protein which is taking part in that reaction. Aromatic amines, on the other hand, undergo the same reaction at the lower temperature to give us a diazonium salt. Now, this diazonium salt is actually very useful for the synthesis of a lot of compounds which are required, rather a lot of aromatic compounds. And notice this is actually quite stable due to the presence of a benzene ring. Normally you would have learned about the diazonium salts, but because it has been excluded from your syllabus this year, you do not have to learn about that in detail. Now, secondary and tertiary amines will also react with nitrous acids in different manner. So reaction with nitrous acid is also used for us to differentiate between aromatic, aliphatic amines as well. And not only that, they are able to differentiate between primary aliphatic, secondary as well as tertiary amines. Next is reaction with aryl sulfonyl chloride. So aryl sulfonyl chloride is C6H5SO2Cl, and this is called as Hindenburg's reagent. And what happens is primary and secondary amines react with benzene sulfonyl chloride to give us sulfonamide. So here we have the reactions. So benzene, primary amine is reacting with benzene sulfonyl chloride to give us N-ethyl benzene sulfonyl amide. So here you have a hydrogen atom attached to the nitrogen atom. On the other hand, when you have a secondary amine, it reacts with benzene sulfonyl chloride to give us NN diethyl benzene sulfonyl amide. Sulfonamide. Here, notice you do not have a hydrogen atom. And this hydrogen atom attached to the nitrogen is very important. The reason being, this hydrogen is very acidic in nature. And this is because of the presence of the SO2 group, the sulfonyl group present here. So that makes this hydrogen acidic. And because it is acidic, it is soluble in an alkali. Whereas this, due to the absence of the hydrogen atom, is not acidic and it is insoluble in alkali. And this helps us differentiate between primary and secondary. However, tertiary does not even react with benzene sulfonyl chloride. And so this reaction is quite useful for us to identify primary, secondary, and tertiary amines. Now, benzene sulfonyl chloride is actually replaced by para-toluene sulfonyl chloride as well. So basically, para position, you have a toluene group attached to it. So primary, you have a formation of N-ethyl benzene sulfonamide. So, and secondary, you have N and diethyl benzene sulfonamide. The difference between these two is the presence of hydrogen atom here and the absence of it here. This hydrogen atom is acidic and this makes it soluble in alkali, whereas this, there is no hydrogen atom, so it is not soluble in an alkali. So in tertiary, it does not even react. And this particular reaction is actually useful for distinguishing as well as separation of primary, secondary, and tertiary amines. The last one is electrophilic substitution. Now, NH2 is an electron releasing. If you remember, we've seen the resonance structures, and because of that, you have the negative charge at the ortho as well as the para position. And NH2 actually activates the ring so much that you get a mixture of products. Aniline also does not undergo Friedel-Crafts reaction, and because of the formation of salt with aluminium chloride. And the aluminium chloride is actually very important because it's the catalyst of a Friedel-Crafts reaction. So let's start with bromination. Aniline reacts with bromine and water to give us a 2,4,6-tribromoaniline. And this is a white precipitate, and this reaction is so quick and it takes place at room temperature. And this is an issue because when we want a single substituted product, that becomes quite an issue, right? So what we do is we convert this NH2 to an acyl group. So what happens is an acetylation reaction takes place first. So when this group is acetylated, the reactivity of the ring decreases, and this gives us the para product as the major product. And obviously you have the ortho, it can't take place because of the bulky groups. They are protected. So basically we are protecting the amine by acetylating it, and this leads to a formation of one of the products as the major product. Now, the reason we are getting only one of the products as the major product is because the lone pair of electrons of the nitrogen atom is going to stabilize the carbon, or rather is going to undergo resonance in this over here itself. It is not going to be in conjugation with the benzene ring. This further deactivates the ring, and this makes sure that the NHCOCH3 is actually less, makes the ring less active than the NH2 group itself. The next one is nitration. Now, nitration reaction is actually quite difficult because HNO3, when it reacts with the aniline, it leads to the formation. It basically partially oxidizes the ring and gives us a black mass. So it is leading to the formation of a black mass. So under specific conditions, you get 51% of para product, 47% of meta and just 2% of ortho. Now you'd be thinking, it does not make sense, right? The electrons are actually present in the ortho and the para. So if anything, we should get the ortho and the para product as the major one. The meta should be minor, but that's not the case. So the reason this is the case is, this is observed is because in a very acidic medium. Now remember, aniline is also acting despite the fact that it's not as basic as the ammonia. Aniline is actually quite basic. So what happens is, it is in the acidic medium, it will form an anilinium ion. This anilinium ion is meta directing, and because of that, we have quite a large amount of meta product. I'd like to repeat it again. Aniline is a base. So in an acidic medium, a strong acid like HNO3 and H2SO4, in a strongly acidic medium, it is leading to the formation of the anilinium ion. And this anilinium ion is a meta-directing group. And this in turn made sure that we have one of the major, a significant amount of the meta product formed. Now, when we have the amine group getting protected, we get the para product as the major product. So aromatic amines also undergo sulfonation. So aniline reacts with concentrated sulfuric acid to give us anilinium hydrogen sulfate. Now, this anilinium hydrogen sulfate is heated with concentrated H2SO4 at 453 to 473 Kelvin to give us para-amino benzene sulfonic acid, which is the major product. And this para-amino is also known as sulfanilic acid. Now, this Zwitter ion, I don't know if you people remember this, but you learned about the Zwitter ion in amino acids. So here you have an NH2, which can take a proton, and SO3H, which wants to lose the proton. So this leads to the formation of a Zwitter ion. Zwitter ion does not have, overall, it does not have a charge. The NH3 has a positive and SO3 has a negative charge. So with that, we're done with the reactivity. I will just go over bromination again. So bromination, first of all, basic idea you have, I know that, but the NH2 group is protected by the formation of the acetyl or is acetylated to give us this NHCOCH3, which makes sure it does not activate the ring as much as the NH2 group. And this makes sure that we get the para product as the major product. Now, these resonance structures show why the NHCOCH3 is not able to activate the ring as much as the NH2 group. That's because the lone pair of electrons are not in conjugation in case of the acetyl group. Next is going to be nitration. We know that nitration in the presence of, it takes place in the presence of HNO3, and HNO3 is oxidizing it to create extent. Now, not only that, at specific conditions, when we do the reaction, we are getting meta product as one of the major products. And that's not usually observed because the NH2 group is actually ring activating in nature. And so the ortho and the para positions are going to be having a negative charge. But the reason this is observed, especially in nitration, is because of the presence of a strongly acidic medium. Aniline as such is a base, and it will get protonated to form the anilinium ion. This anilinium ion is actually meta-directing and not ortho-para, and because of that, we get the meta product as the one of the important products which are formed. Next is sulfonation. Sulfonation, you're having formation of anilinium hydrogen sulfate, which on further heating with concentrated H2SO4 is giving us sulfanilic acid. Now, this sulfanilic acid can exist as a Zwitter ion because SO3H wants to lose the proton, and NH2 can gain the proton. With that, we're done with the various reactions of amines. I have covered the maximum that I could. If you have any doubts with these reactions, to reach out and I will try and clear out the doubts. Uses of amines. I was actually really surprised that this topic was there, and I noticed that the uses were included in the syllabus, and when I was shooting the syllabus part of this video. And I went back to the textbook and I started looking for it and I could not find it. And then I went back to the introduction and noticed that all of this is actually given there. So the introduction itself has the uses of amines. So amines occur in proteins, vitamins, alkaloids, and hormones. Alkaloids are very important. basic definition of an alkaloid is a compound that contains nitrogen. And if you Google alkaloids, you have so many alkaloids which do exist in nature around us, and they are very important to us, and we don't even realize it. Other examples of amines include synthetic examples like polymers, dyes, drugs, and nitrogen is present in all these, obviously. There are two biologically active compounds, adrenaline and ephedrine, and they have a secondary amino group, and they're used to increase blood pressure. And novocaine is a synthetic amino group, which is used as an anesthetic. Benadryl, an antihistamine drug, antihistamine, and quaternary ammonium salts are used as surfactants. So with that, we're done with the uses of amines. We're done with the whole chapter because this year you do not have diazonium salts. It's not included in your syllabus. For this year, 2021-2022, you do not have to worry about the same. So with that, we're done with the amines. We started with the nomenclature, or rather we started with the structure, then we moved on to the classification, nomenclature, preparation, physical and chemical properties, and we finally finished up with the uses. With that, we're done with the whole chapter, and if you do have any doubts, do reach out to me, and if I've missed out anything, do reach out and let me know. And the notes of the same will be in the form of PDF is given in the description below.